Welcome everyone to a new session of MIST101. I'm Nick. I really appreciate that you can watch this video because everyone is busy with their midterms and assignments. So this session workshop will be a shorter one, and let's get into it. In this session, we're going to be talking about um, how to make the model fit. So essentially, we want the model to have the best performance when doing the training. Okay, so from last session, we've introduced a biological neural network, and we talked about the connection between a biological neural network and an artificial neural network. There are similarities in how we as humans created artificial neural networks from the idea of how our brain works. And we also talked about neural networks architecture for example, in this graph, and the activation functions. So for activation functions, here's a quick recap: is that how you calculate the output, like these outgoing arrows from all of these the arrows coming into this neuron. So how this neuron collects all of their inputs and use the activation function to produce an output. And finally, we talked about feed-forward and backpropagation, where in feed-forward you just feed some data into this network and you get a result. And for backpropagation is the mechanism for us to update all of the weights in the neurons, and we can train this network to make a better prediction. And backpropagation is very complex in terms of concepts and math, so we didn't cover a lot in that. It's more like a beginner introduction to an intuition how backpropagation will work, and why is it important in training a neural network. But in order to build a neural network and train on it, we don't need to understand what backpropagation, like what it really does, because there are already built-in functions in a lot of the libraries. So you just need to know that for backpropagation is a process where we want to update all of the weights. And yeah, so into today's schedule, we will be introducing overfitting and underfitting, where I mentioned once in the second workshop, so 1 month ago. And we will be talking about methods to prevent overfitting. And essentially, there are two very important, which are called regularizations and early stop. I will be focusing on these two. And finally, we will have a coding tutorial on PyTorch once again in order to figure out how exactly do we do in code. I think that's what you guys are mainly interested about, to produce the best performance, right? So last time, Shubra did a demonstration on how to use the code to build a model and run and finally come up with a result, right? But in this session, we'll be more focusing on how to produce the best performance from by updating the parameters, and we want to get an idea how to look at the graphs and the result in order to know how the model is performing, and when do we stop the training, and when do we know the training is done and the performance is the best. Yeah. So remember, previously we've looked at these graphs where the red line is the function of the model, or you could think of it as a prediction of the model, and the green line is the ground truth, where these blue points are the data we get with some sort of noise. And among these, for polynomial function, we have 0 degree, 1 degree, degree 3, and degree 9. And yeah, and we ask a question, which function fits the best? And essentially, the two questions asked is, does the best fit in your mind make sense for this model? For example, we said this was a price prediction model, right? If you have a shape like this, does it really make sense for a price prediction for a stock price prediction model? And we have this second question: does the best fit model generalize to other data? Like generalizability is a concept that I kept emphasizing because you essentially want the model to generalize to other data from your training. So that's very important. And you want to ask yourself always, like, does this model generalize? So of course, our conclusion is that the degree 3 one is the best because it fits the ground truth most. Degree 9 in this case passes all of the data points we have in the data set, but it's not necessarily the best one because look at the ground truth, right? It's doing a lot of unnecessary complexities here. So this one's not the best. And yeah, performance measurement is what we're looking at here. How the model perform, and that would take us to the concept of overfitting and underfitting, because these two terms are indicating that how well the model is performing. And I'll get straight into that. So for these two cases, they are called underfitting because clearly the model we have does not fit the function. It's too simple, so it's called underfitting. And in this case, it's called overfitting because it's really doing the over, and the model is too complex to fit this data we want to have, and it's just not appropriate. Even if it passes through all of the data points we have, it's not the best representation of the true data. So it's too complicated. Okay, so in real life training, it's often like more likely we get an overfitting situation than an underfitting situation, because as we train more train more iterations with the models, we would have eventually a very complicated model to fit all of the data points, because we can only use the data set we have to train the model. So as the model learn more and more, it will just learn how to fit exactly to make a prediction on those data points, but not generalize to some other data they have not seen, right? So as you train more, overfitting is what you will get eventually, and underfitting will usually occur only at the beginning phase of your training. So, but in this case, we're using the polynomials to represent the model we have. But in neural networks, it's much more complicated, and so you can think of the model complexity is increasing from a 0 degree to a 9th degree polynomial, just as an example. Okay, so next, we want to explore the difference between overfitting and underfitting. So if we only look at a small range of X, we only have a small portion of this graph, for example. What is the difference between underfitting models and overfitting models in terms of distribution of prediction results and ground truth? So I will just narrow the graph to this very short period of X. And you can essentially look at the red line and the green line and see what's the difference between the underfitting case and the overfitting case. Yeah, take 1 minute to think about it. You can pause the video here. Okay, so from observation, we can easily see that the red line is nearly all of the red lines above this green line, and there's a lot of deviation here. And you can tell that constantly in this range, the red line is the prediction is much higher than the ground truth, and of course it's not an accurate prediction. But in the overfitting case, the red line is going beneath and above and beneath. So in this case, when you're making a prediction, it's like up and down. Making prediction around the ground truth, but very few of the points can actually be hit exactly on the ground truth. So they are totally different. This one is consistently making a wrong prediction, and this one is sort of um, going up and down, scatter around the ground truth. Um, but with some occasions, it will um, hit exactly on the ground truth. But that's just a very small probability, right? So this graph may be a better demonstration of these kind of behaviors. For underfitting, we're looking at high bias and low variance prediction results. So for example, this is the point you want to hit, or the ground truth, but you are making a prediction with a large offset here. But every time when you make a prediction, it's pretty consistent with a big error there. So you see there's a high bias because the prediction is wrong, and but there's a low variance, which means that the prediction will all be squeezed here at this wrong point. But for overfitting case, you have high variance and low bias. So you make the predictions all scatter around the sender, which means that it's all false, but it's still around the true, like the ground truth point. It's like it's just scatter around it. But the sender of your predictions are correct. So you're still not be able to create a good prediction. It's just this more scatter around. Yeah. So these two demonstrates how underfitting and overfitting um, characteristics are. Yeah, and also we want to know how to detect overfitting and underfitting. Remember, in workshop 2, I introduced these representations of data set, like how we split the data set in order to look at the performance of the model and how we actually train with this data set. We want to have testing sets separate in order to test the final accuracy or the result of the model. But during the training, right? During the training is the actual process, like when we want the model to perform the best, and we want to adjust the model constantly in order to make it the best performance before going to test it with its testing set. So we have two ways to do that. First is we will split out another small portion called validation set. So you never train using the validation set once again. You only train on the training set, and you use the validation set only to validate if the model is making a good predictions and has a good performance. And so if you have a training and validation split, then you will always be training using the training set, and you will be validating every iteration using this validation set in order for you to know that whether the model is actually overfitting, as we were talking about before. And in cross-validation, it's the full utilization of this training set. You split the training data into a lot of folds, we say, and each portion here can be a separate validation set. So you essentially validate on each of these once, and then you will get an result of the accuracy, the validation accuracy. Okay, so here we have a small quiz. So looking at these four combinations of training accuracy, validation accuracy, and testing accuracy, right, which of the following result do you think is the best? So in last session, we have already looked at how to train with neural networks, and we have training accuracy and validation accuracy calculated at the end. So based on your own intuition, when you're doing the training, if you see these numbers, like what does it tell you? And what do you think the model is best? So think about overfitting and underfitting in this case. So you want the model to generalize, but not to overfit. on certain um, data you have. So think about it for a minute. Okay, so the result is actually the option B here. And if you look at the other ones, for example, in A, you have a training accuracy of 99%. That's very good. It probably means that your training has covered all of the data points, and it could make prediction directly exactly on the data points you have. And the validation accuracy is also very high, it's 98%, but you only get 80% test accuracy. So you'll be very surprised why you have such a good training process and you have a good validation accuracy. But why, when you're testing on a testing set, right, you get such a low accuracy? This is not an unusual thing, and it's probably meaning you have some error in your training. So if you look back, it might be the case where you your validation set um, is very small, so that the model just get lucky and makes some more good prediction, so you get a high accuracy. So in this case, if you see this scenario, you might want to think, oh, what's wrong with my training process? You might go back and look if I'm actually overfitting the model. Right? For C, we have training accuracy of 90% and validation accuracy of 85%. So that's from the look of this, it's it's decent, right? We have a training accuracy of 90%, which means that the model is actually learning and can make good predictions, and the validation accuracy is still very high. It's very reasonable, but you only have you have a test accuracy of 95%. So in this case, similar to case A, it's probably that you get lucky on a test set where you have maybe just, for example, 10 instance on the test set. So if you have one more good prediction, like the accurate correct prediction, then the accuracy will increase by 10%. So that's a lot. So it might be you're getting lucky with with the test set and the test accuracy. Um, so you might want to increase the number of data you have or readjust the split in order to get a good indicating numbers here. And for D, you have a training accuracy of 70%, which means that the model is not learning as well. So the model is still in the process of learning, but you see a validation accuracy of 100%. So that might be a case where you get lucky with the validation accuracy. But if you only stop here, if you stop here, you think that, okay, the validation accuracy is fairly high, I can stop now. It's probably just because you're getting lucky in this iteration when you are validating on the validation set. You get a very high accuracy. But probably in the next iteration, you will get a accuracy of 80% or 70%. So you need to keep going. Don't stop just right here when you see a very high validation accuracy. So and apparently the test accuracy is only 60% because you have not trained long enough yet. You just stop very early when you see a lucky result on the validation. So the final answer here, 95% for training accuracy and 94% on the validation accuracy means that you're training very well and the model is not um, overfitting that much to, for example, like 99% because these two numbers are very close. And you finally get a test accuracy of 90%, which is still very good. Uh, So that's the most reasonable case, and it's probably a number when you look at it, you think, okay, I might be doing the correct thing. I don't need to go back and readjust my model training. So Here, if we only say, okay, test accuracy is the only metric we're going to look at when we want to decide whether the model has the best performance, then you're probably going to be wrong, because when the test set is very, very small, you might just get lucky with it. The model just get lucky with it. Like make a few more correct prediction, you get a very, very high test accuracy, but it doesn't mean that the model can actually generalize to other data. So always make sure that you have enough data points in your each of the set, and make a good split on them, a splitting ratio on them. And yeah, when you see a number like in B here, it's probably reasonable and good. Okay, and there's another concept called Ocams Razor. Um, so in philosophy, I suppose there exist two explanations for an occurrence. In this case, the one that requires smallest number of assumptions is usually correct. Another way of saying that the more assumptions you have to make, the more unlikely an explanation. So how do I understand this? My intuition is that if you and another person want to explain some concept or some technical um, idea to a person who doesn't know, the other person's explanation uses paragraphs of assumptions, ideas, and evidence, and there's a lot of deductions in it. And finally, he came to a conclusion, right? How this concept works. But for you, you only use one sentence, and you can explain the concept. So both of you can explain a concept to that person. That person could understand both of your explanations, but it's more likely that your explanation is probably correct, because you use only one sentence. That's simple, direct, and it should be precise enough in order to explain that concept. And in machine learning, it means that if two models have comparable performance, then you should usually pick the simpler one. For example, if you just want to model a very simple thing, for example, acceleration and position, when a car is moving, for example, you could just use a quadratic model to model it. Like you only have three or four parameters at most in order to model that. But the other person could say, okay, I will use a neural network of 20 layers and thousands of neurons in order to model that. It's totally not necessary to model such a simple thing. So both of you can have the ability to model one thing, but the simpler model is usually the more correct one, because it doesn't increase the complexity in the model, and there's not much to interpret really in that situation. Okay, so in the next slide, we'll be going into the methods to prevent overfitting. There are many methods to prevent overfitting, but you don't often see methods to prevent underfitting, because as we often train more on the model, we will more likely get overfit instead of underfit. So if you are in the underfitting situation, simply just train more and let the model get the prediction close to the data you have, and eventually it will become an overfitting situation. But we definitely need to know how to prevent overfitting, because we want the model to stop kind of before it overfits, or from the very beginning we don't want the model to overfit in the whole training process. So there are a lot of methods to do that. The first one is cross-validation. We've already discussed this in the previous sessions. And for cross-validation, you just simply split the training set into multiple sections and then use each for validation. And then you know how the model is performing, how the accuracy is doing. And that's a good way to know how to stop overfitting. Yeah, and the second one is train with more data. This is also called reduced bias. So a very simple but not appropriate example is, for example, you only have three data points for a data set. And you are training a very complex model based on only three data points, and that is ridiculous, right? It's very likely that there is very high bias in the three data points you have. But if you have 3,000 or 3 million data, then those data will probably cover almost all the cases, and there will be less bias, a very minimal bias. So if you train with more data, the model would less likely to overfit to some kind of bias or data distribution. So you have more generalizability in your model. The third one is reducing the features in dataset. Um, we talk about features in a dataset is those kind of the attributes of each of the data point. And if we can reduce those kind of attributes, reduce the features, then your model will less likely to overfit. Um, we will discuss this in the next slide in detail. Um, And we also have regularizations. Um, so regularizations, very simply saying, is that it's a term you add in the cost of your model prediction, and it will help your training to not getting to a very overfitting situation, because you're updating the model based on the cost, and we're just tweaking that cost function a little bit. So it's a trick to use in order for the training not to overfit. Finally, you have early stopping, which is a very practical method in training, and we'll be looking at early stopping in the code demo later. Yeah, and the first one I want to focus on is reducing the features. So for a data set with n instances and d features, if we want to train only with linear models, right? Um, so there's this case. If n is larger than d, so you have more data points than the features, then it's very likely that your linear model would underfit, because there are essentially just so many data. You cannot adjust the linear model in order to go through, like, in order to fit exactly every data point. But in the other case, if you have less data points than features, so n smaller than d, it will be a situation where it's more likely to overfit. Because, for example, if you only have one or two data points in a data set and you have 10 features in a data set, well, it's very easy to model these two data points. So it's very easy to overfit. Well, but to fully understand this concept, like in mathematics, like how you prove these, it's you will basically see this in the fourth year course. Um, and you'll be exploring more with linear algebra and and calculus there in order to understand this behavior. And another way to reduce the features is called principal component analysis, or PCA. It's a very popular um, technique in data science, and Shubra will talk about this in the next workshop when she will be doing the unsupervised learning. So next we'll be moving on to regularizations. So we could fit a polynomial to the data. The polynomial may be an nth degree polynomial, and for each term we will have a coefficient, right? This will be all of the weights or parameters we have for our model, all of the w's. But we might not necessarily need to use all of the degree here. For example, we could just have the first two weights and assign all of the others to um, 0, right? So in this case, it will be a um, sort of like a linear model. But you could definitely assign weights to other degrees terms. But the higher degree you have, um, it means that the model is more complex, and there is a likelihood that you're going to overfit with a very complex model. But if we look first at the error calculation here, um, you simply put this your model function, this y, into the calculation, and t is the ground truth or the label of the data, and you make a difference, then you square and you make the mean. This is essentially the mean squared error you have when you're calculating the error. So usually you calculate in this way, and your goal of training is to minimize this error, this cost function. But how do we know degree 3 is probably the best polynomial to use? For example, we only use the first 4 parameters for the model and just assign 0 to all of the other degrees. But how do we know that? Can we actually do that? So remember in this graph, if you have a degree 9 polynomial, it will be very, very complex, and it's definitely overfitting. But for degree 3, it's the best one. So how do you actually minimize the degrees up to 9, for example, from 4 to 9, and you minimize the coefficients for those kind of terms, and make the model as simple, but not as simple as these. For example, 0th degree, the 1st degree. These modeling is just too simple. But how do you do that? So the technique here is that we could add another term to the cost function, right? This term is called a penalty term, because you essentially want to penalize when the cost function when the model is too complicated. But how do we do that? Is we add a term, we use lambda, a constant, times whether the L1 or L2 term of this whole weight vector. So this W here is the vector of all of the coefficients, and you can calculate the sum of the absolute values or the sum of the squares of all of the weights. So what's the intuition here is that if you have very, very large number in some sort of parameters, or your model weights is very, very large, it probably indicates that the model is very, very complicated. Then your cost will be bigger. Your cost will be large. So you want to minimize both the original error calculation we have and this penalty term. You want to minimize the both in order to have a lowest cost function in your training. So with this penalty term added in during your training, your model will not have a very large coefficient or sum of the coefficients in the terms. So the model will not be overcomplicated. So this is a trick to use when you want to prevent overfitting. And in neural networks, this method is called weight decay, which means that we want the weight to be small, but not to explode. For example, you have 0.1, 0.2 for 9 of the parameters, but you have 1,000 for another parameter. This is not good. So this whole term will penalize this kind of weight distribution and make your model a simple one and the best fit one. So if we only want to have the 3rd degree in this case, well, you will still have the coefficients for all of the higher degrees, but for example, from 4th degree to 9th degree, those coefficients will probably be very, very small, so that you still see a function sort of like a third-degree polynomial, like this. That's the magic of this regularization term in a very simple way. And the final method is called early stopping, which refers to stopping the training process before the learner passes the point. So how do we understand this graph? We'll be seeing this graph later in the code demonstration. But how do we understand this? That we have a training set, and we train the model use the training set. Of course, as the number of iterations goes on, we will train the model better and better. The model will become an expert at the training set. But the model has never seen validation set in its training. So at first, the validation error will go down, apparently with the training error, because the model is learning. The data is not some random prediction anymore. But after some point, you will see the validation error increase again. Oh, it will not be this steep usually. It will usually be a curve like this. So you'll see gradually the validation error will increase after some point as the training error is still going low, which means that your model is trying its best to make the prediction as close as to the training data points, but it doesn't necessarily generalize to the validation set or other data it hasn't seen. So the validation error will eventually go up as you overfit to the training set. And we want to stop it right here before the validation error goes up, which means that this point is probably the best point we want to have in a training, so that the model has the best performance, the best ability to generalize its prediction to other data. But you might ask, okay, the model is keep updating. We can't know this is the point to stop unless we go past a few iterations after it, and we see a upward going direction, right? So in this case, you will want to save your model very often. For example, save it every 1,000 iteration or every 100 iteration, so that you will constantly have the checkpoints here, 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 here. And once you see that, okay, the validation error has gone up, you will go back to the point where it's the lowest and use the checkpoints somewhere here. So you take that as your final model. Yeah, so that's all for the parts for the methods of preventing overfitting. So from just the introduction to the concepts, it may not be very intuitive. So we're going to use the code in PyTorch in the Google Colab to show you how this process works. And this early stopping graph is what we want to look at there. And that's all for the workshop part of this session. And thank you very much for watching. And please ask any questions if you have, or leave any comments in the video so that we have feedback from you. Yeah, so any sort of suggestions or questions are welcome. So thank you for watching.